Well, thank you for that welcome. Well, my name is Arjan Scherpenisse, and like I said, I join you from the Netherlands, from my current office in Almere. My talk is today is about creating a scalable intent classifier using Elixir-Python and Tensorflow. A very long title, but I'm gonna touch all subjects, so don't worry. In this talk, I'm going to talk about a bit how our intent classifier was implemented with the help of Elixir. So this is the agenda for the talk for today. So first, I'm going to start off with a bit of context. So why am I actually interested in this subject? Then a bit theory about what intent classification actually is. And then I'm going to show how to implement this using Python and to see how it performs and what kinds of issues we are getting when we do it just with Python. And then I'm going to talk about how I use Elixir to, well, as was already said, orchestrate the Python the processes. And in the end, I'm also going to touch a bit upon some future work that I'm currently researching, because since I started this project, the machine learning landscape in Elixir has changed quite a lot. With the Exxon and NX libraries that are out. So let's get started with a bit of background. Well, my company Botsquad is can be described as a low-code platform for conversational apps, and the company is now actually part of Enreach, which is a bigger telecommunications company. So that's why I'm now in a pretty big office where I used to be in a very small office. So what is Botsquad exactly? We host a platform on which we and others build conversational apps, also sometimes called chatbots, for all kinds of different channels. So for instance, there are the channels on the web widget where you can start talking to a bot and then later to a live chat to customer support, but you can also do that through the native channels like WhatsApp, messaging, Facebook Messenger, etc. And since a year or two, we also support voice channels. So, for instance, the Google Home and Alexa smart assistants, but more interestingly, the old traditional phone line systems. We, for instance, have one service where doctors, where you can call a doctor and they get a robot on the phone, and you can ask to make an appointment for you. And it's not a very dumb robot like press 1 for Monday, press 2 for Tuesday, but it is much more naturally. Although it of course still remains a chatbot in the end. To give a bit more of context, this is a bit how the platform looks internally. So on the top, you see a lot of different channels that I just talked about, all different kinds of adapters that hook into our runtime. And in the core of the system are bots, and the bot engine is basically driven. Well, I'm not going to go into much detail today, but it's driven by a small programming language where you can script the bot in a very simple way. And besides that runtime, there's also an environment where you can actually develop these bots. So that's like an IDE environment that is at the same time also suitable for people who are just interested in editing the content of the bot or just managing it, looking at conversations, how they went, viewing analytics, etc. So it's there's a lot going on in there. But what I'm going to talk about today is actually the NLU part, and that is the part where the bot tries to understand what the user is actually saying. NLU means natural language understanding. So when looking at natural language understanding, there's also quite some technologies that are in play, and usually those form some kind of pipeline where users' input is transformed into something that we as a programmer can use to infer about what the user really wants. So our NLU pipeline looks a bit like the following, where the speech of the user is transformed into text actually by the Google speech-to-text service, which is a really well-performing speech-to-text engine. There are also some open source speech-to-text adapters, but those are usually, well, less good, unfortunately, still. Also in different languages. English is usually quite good, but we are in Europe, so we need to deal with a lot of languages. In NLU, there's also usually a pre-processing stage where the text that is recognized gets gets analyzed and detect what kind of language it's spoken in. What are actual words? What are the sentences? Are there any like interesting parts like dates or times mentioned, etc. And then usually an intent classifier is run, and that's what this talk is about. So the intent classifier is a mechanism, is a model where there are some. Well, let me first say a bot always has a purpose. So the bot can only. Sometimes people ask, "What is? Can this bot learn by itself? Can it? Is it the real self-thinking entity?" But the answer is, unfortunately, or maybe luckily, no, because it is still, something that a user or administrator manages, and it has a certain set of functions. So in those functions, to map what the user is trying to say until what the functions of the bot are, those are the intents. And so to be able to understand what the user is saying, we use an intent classifier. It's basically a set of labels that describe what the user wants and what we can do with it. And then those intents are usually used to kick off a part of the conversation. So for instance, if we understand, we want to open a bank account because the user said, I would like to give you some money because you're a bank. Then the intent is open bank account, and we kick off a part of the conversation that is about opening a bank account. So that is the part of the dialogue resolver. And so for this natural language stuff, there's actually quite a lot of libraries and technologies that you can use, because this is AI and there's an AI hype. So there's a lot going on. And we actually also use a lot of different things. And I already mentioned the Google speech-to-text engine. But another one that's very notable is also Spacey. That's a very nice Python library that deals a lot with text mangling and analyzing different languages, etc. Another one to notice is Dialogflow, which is also a Google product. And Dialogflow is actually a commercial intent classifier. So we used to use that a lot for when we did not wrote our own intent classifier yet. But it was quite hard to manage. So after a while, we started writing our own intent classifier, and that is the Q&A Ninja as we dubbed it. I don't really know why I added the Ninja part there, most probably because there's a .ninja top-level domain, which I really liked. The Q&A Ninja was initially meant for just answering questions of a user. So there's in the bot CMS, there's a part where you can basically manage a frequently asked questions section and add some phrases to it, and then the bot trains it, and we put it through the Q&A Ninja, and then it gives you the right answer to the question of the user. But it turned out to work pretty well. So we started using it more and more. So what is actually intent classification? I already touched upon it a bit. When a user says something, it's human language is pretty complicated. You can say the same thing in 100 million different ways. And those are all different kind of sentences. So from beforehand, as a programmer, you can never know how a user is going to approach a bot. It's not just a matter of presenting a button and the user can click on it. And you can basically say anything. And that's also what makes chatbots really hard, and also quite hard. So as we have seen, intents can be seen as clusters of similar sentences. So they are user sentences that are close to each other in meaning, and we can somehow group them. So here in this example, you see 3 different clusters. One is about, this is an example from a banking training set. So on the bottom left, you see something about top up, add some money to a card or something. Then there's something about card delivery, different sentences related to that. And there's something about, no, it doesn't work. Please fix it. And those intents, we give them a label so that in the code, we can later say, okay, for this label, we need to do this part of the dialogue. And so if you look at this, was it something? Oh, never mind. I heard some noise. So if you look at this, you can actually view each of these sentences as a point in space, because that is a bit what it is. If we want to be able to do anything machine learning related to this, we need to convert these text into numbers, because otherwise we cannot use it for anything. So so usually what is done is that sentences are translated into what we call feature vectors. And in this example here, it's a 2-dimensional space, but in practice, actually, you cannot really picture these feature vectors as a real image, because they are really high dimensional. Something like 512 dimensions is very common for a single feature vector. And the number of how many dimensions a feature vector has is actually very dependent on how that vector was obtained. And what an intent classifier then does, it takes when a user says a new sentence, then we transform that sentence into a feature vector, and then we check which of these clusters that we know about, which is our trained intent model, which of these clusters is the closest to my to the thing the user just said, and then that intent gets also a probability. So we think that it's very, very close. So the probability is almost 1. And that way the intents are ranked according to their proximity. And given the input data of these utterances and their intents, the classifier really trains some kind of machine learning model on this data. So how do we actually get from a sentence into something that we can use in a mathematical way, into a feature vector? Well, for the most simple one is actually bag of words, word to vec, it's also called. It was a technology made, I think, popular some 10 years or something ago, where basically you have a really large set of training data, and you basically just count the number of occurrences of a certain word. And every word is a dimension into this really high dimensional vector space. And by doing that, you get basically a histogram for every word, or for every sentence. You can build a histogram with the frequency of how much the words occur in the data. But the downside of this is that it really requires a really large amount of training data, because otherwise it does not really make sense. If you just have a few words, it also does not really know about synonyms, or about the order in which words occur, or about ambiguity. So a word can mean, you can sit on a bank, but you can also put money in a bank. A bank is not the same bank as in the other sentence. So this is a pretty plain, simple model, but right now there are actually better models available, and those are usually what we call pre-trained language models, pre-trained neural networks that are basically already there for you to help to make a feature vector out of something. And one of them, actually the most popular one, I think about 3 years ago, it was made by Google. It's called BERT. BERT is, I don't really know what the acronym stands for, bidirectional encoder transformation something. Actually, it's a really big language model. It has something like 340 million parameters that all need to be kept into memory. So it takes up quite a lot of memory. But it is trained on basically on all text on the internet. So it has Wikipedia It has been looking at Wikipedia and all languages and at Project Gutenberg and all the news websites. So it really has been trained on the text, and it has done this in an unsupervised way, which means that it was given a text, but they then left some words out basically, and then they trained the model in a way that it would predict the right word on the gap where they left the word out. Well, it's a pretty big subject, so cannot go into much detail here. But it suffices to say that it works pretty well also for ambiguous words and context-related words, and then actually another version of BERT that is even more suitable for short sentences, called sentence BERT. And sentence BERT is a collection of models which are really optimized for creating classifiers based on short sentences that are given to the model. I've put some links in the slide note, so if you're interested, you can always read more about it. This is BERT. There's also an Elmo, and there's a lot of other characters out there, and these scientists always give they try to come up with really funny acronyms for their research papers. And BERT is the most famous one, I guess. So how to create an actual classifier from this? So we have a sentence, we make a feature vector out of it. We just discussed that using any language model that you can use that's suitable for you. And then those feature vectors are basically given to some kind of neural network. And that neural network is actually there's also a lot of different ways how that neural network can be shaped. But for most purposes, I think the simple feed-forward neural network could work pretty well. So that's basically a classification problem that is not different from classifying a set of handwriting characters that Jose Valim showed in his NX demo. Or any machine learning problem can get a classifier at this point. Whenever the sentence is featureized, it's just a vector in a space that can be classified. So it becomes pretty generic and a well-understood machine learning problem. So how do we do this in Python? So when I started with this, I thought, well, I know a bit of Python, and for data science and machine learning tasks, it's a real obvious decision because there are so many libraries, and basically everybody in AI is settled on using Python right now. Still, maybe it will change in the future. But right now, Python is basically the go-to for anything related to machine learning. So before we start doing this in Python, I had a little bit of a training set that I selected for this. And I use it basically as a validator for myself to see the thing that I was developing, whether it would perform still good enough as the reference implementation in plain Python. So I took a banking data set with about 77 intents, and actually a lot of training sentences per intent, like maybe about 188 or something like that. And then I split it into a training set and a validation set. And I didn't use the validation set for training because I then later checked whether the trained model still performed well on the validation set. Because that is a real thing in machine learning. If you basically train too much of on the model, it can actually overfit. So that means that it's really specific to the thing you trained, but it's not general enough that it can classify other correct phrases into the same intent. So that's overfitting is always something that you have to watch out for. And then basically I measured the number of correctly predicted validation samples, as it says there. So if we want to do this in Python, there's actually a lot of options. One of them is Rasa, and Rasa is a Python framework for building and training chatbots. And it can be configured in various ways. And it's basically just a matter of following a few steps, which adding your training intents and training phases to a YAML file, add some kind of config file, and then train it. And that takes a while, the training. And then afterwards, you can run a spin-up Python server, and it exposes an API, and then you can give it a sentence, and it will return an intent with a confidence level. So it was pretty easy to do. So the result that I used, I actually configured it to use the BERT training model, and I got a 91% precision on my validation set, which I think is pretty nice. But it was not really fast, and it was also very slow to train, because this tiny laptop that I have here does not have a GPU, so it uses it takes a lot of time to train. And also for some reason it was pretty slow, because it somehow it was. I also checked with another feature factor method, and it was much faster. So for some reason, the Rasa BERT implementation makes something inside there pretty slow. And of course, because it was using BERT, which is this big neural network, you have to remember, of 340 million parameters that has to be kept in memory. It was pretty big to run this Rasa server and keep it in memory. So that was the results of plain Python. And if I were building a single chatbot for a single customer, using Rasa and Python this way would all be fine. I would train a model and then deploy it, and the Python process would be deployed on a single machine, and would just be there, stand there, classify intents and serving intents for that single bot. But of course, it would take 1.3 gigabytes of my memory. And I'm not building a single bot, but we are actually maintaining a platform where a lot of people build bots all the time. So I wanted a way to run any number of bots in a cost-efficient manner without spending 1.5 gigabyte of memory on every bot that was deployed. It's just basically not feasible. So the question is, how could we solve this? The Rasa team actually, if you want to keep using Rasa, they actually advise, if you have multiple bots, you just create multiple Python processes. And that just does not really scale well. So that was not really an option, because you would have this Rasa model here, and then another Rasa model and another Rasa model, and my memory would increase and increase. So what's also very notable is that the memory-hungry part of this classifier is in the conversion of the sentences into feature factors. The BERT model that I talked about. However, this part is not really specific to the actual bot that is run, because it's basically a functional operation. You take a sentence in a certain language, you get a certain feature factor, and that's always the same, no matter which bot it's used for. So it's not classifier specific, and that part also does not need to be trained. So what I did was I started to reuse that featureizer over multiple bots. So I created a single featureizer and then used it to train one neural network per bot. And this way they can be scaled independently. So before we continue with how I did this with Elixir, I wanted to give a little demo of how it actually looked in our user interface. But I see I don't have too much time for this, but I will do it anyway. So what you see here is the training interface, or actually the Botsquad interface, and that has a training part. And in this training part, you can define some intents, and these intents, they each have a few training sentences. And whenever you make a change to the training data, you can save it, and then a little button appears. Because right now I can actually just try it. Where is my credit card? I don't know, is this actually something? Well, it's actually matched an intent here. So it actually worked, but it gives me a warning because a retraining is required because I just edited a sentence. So if I click train, then it will actually start and give me a nice animation to train the data. And that way, so basically when I change a sentence, it will probably end up here. So if I have a new sentence that I want to add, I can just add it here and it will be added to the training set. And then that intent can later be used in the bot, and it can be actually used for creating a little interaction with it. So and that's actually all I'm going to show. My presenter notes are gone. Here we go. So yeah, so what you see in here was this basically this little interface where you can add intents, and you can retrain it, and you can test intent to see how well the classifier performs. So how did I build this in Elixir? Basically, the Q&A server, as it's called, it's one Elixir system, but it manages a group of Python processes. And some of these processes are used for training the intent classifiers, and others are used for classification of intents. And all of these Python processes, they communicate with a featureizer, which is written as an external service. So it's not really part of, there's not one feature BERT model per Python process in the Q&A server, but there's like an external Python process, or multiple actually, that do the hard work of and the memory hungry work of converting text into a highly dimensional vector. And after a model has been trained, it is stored in a zip file on Google Cloud. And then later, when a request comes in to classify a sentence against a certain model, the classify Python process loads this from Google Cloud again, and it remains inside the Python process for a while there. So let's dive in into some of these components here. Like the featureizer microservice that was on the right of the graph is a very simple Python script, and this is like a demo implementation, not the actual implementation, because it also does a bit caching, etc. But Python makes it really easy just to make a little HTTP server and then get something. So it exposes a route here, encode, and encode takes the Q argument from the request and then encodes it using this sentence transformer, which is this sentence BERT library that I talked about, which gives us a vector. And that vector is just returned as the HTTP response, as a pickled format. And pickle is Python speak for term to binary and binary to term. It's the equivalent in Python. So it dumps it in a format that is convenient for the other Python process to read it back in and process it further. Because under the hood, this uses the NumPy library, so it's a NumPy array, and I could also have returned JSON, but that would be really rather inefficient. The Q&A server is actually a lot more interesting than the featureizer. It consists of a plug router, which serves all the HTTP requests, and then two supervisors, which are responsible for a number of these child worker processes. And all of these processors, these trainers and these classifiers here, they are external, or they are gen servers, and each of them manage a single Python program. And that's actually done using a library called EarlPort. So EarlPort is a library that allows you to spawn, I think, also Ruby and Python processes in a very easy way. And and handles the marshalling and conversion of terms from Elixir to Python and back. So basically what happens here is that under the hood you can just start a Python process, and then you can call a Python function, and the result would be returned in your Elixir code when the function in Python is executed. So there are two programs here that are being run, and they are run a number of times, because we basically run it one process per CPU core, so that it can scale pretty well. So on the HTTP side, there's some routes where actually the model name is the key in which everything is sharded, and so the model is basically the ID of the bot in most cases, or the ID of the bot plus the language, something like that. So for every bot we can have a different model. So the predict route is probably the most important one, the predict and the train routes. And there's some nice diagram here that's maybe a bit, I don't know if this is very readable, but basically this is also what you saw in the demo that I gave. So there's the training data is posted to the train interface, and then the Q&A server kicks off a Python training process, which does its TensorFlow magic. And then at the end of that, it stores its model. Actually, I have this in 2 more slides over here. So the trainer script actually is one Python process that trains a single model. So it exposes the train function, and that function takes model name and the data. And data is basically just a list of intents with their related utterances. And it also gets the bit of the parent, the calling gen server. And then the Python program itself is actually quite long, but what happens is that it uses the TensorFlow module, and especially the DNN classifier class, to train the data. And the actual neural network that is used, like I explained earlier, is pretty simple. So it's just a 3-layer network with on the input layer a number of neurons that have 1 neuron for every dimension in the feature vector. And then there's an hidden layer in between, and then there's an output layer, and it has 1 output neuron, these orange ones here, per intent. So what happens is that the feature vector comes in, and the weights are the feature vector is propagated to the network, and then in the output layer, different values between 0 and 1 appear, and the one that is closest to 1 is then the one that has been classified. That's the index in the intent array, basically. And what's also nice about TensorFlow is that you can have progress callbacks. So while it is actually training, it can call a Python function for you. So I use this to actually give some feedback to the gen server, and that's why I pass in the parent process ID here, because while it is training, I calculate how far it is in the progress, and then I pass that information back into the trainer gen server, and then that's why you saw in the demo that little progress bar that was increasing like that. And there's also a very handy function. It's called export save model, and export save model of the estimator just saves the model to a zip to a file, and that can be later used in the predictor to load that trained model and actually execute the prediction. So one Python process holds, for the classifier as well, holds a number of models in memory. But these models are actually not so big. They are not gigabytes of memory. And the classifier gen server also has a function called predict. Takes the model name and the sentence, and then a few optional parameters. So it loads the model from Google Cloud, and then TensorFlow basically, when the model is loaded, exposes a Python function where you can pass in a feature vector, and it will return the scored list of intents. And what's also interesting is that the Gen server actually manages the usage of the models. So the models in the Python process are kept in memory for a longer time, because you can imagine when a bot is hot, if there's a lot of people talking with the bot, we don't want to load the model every time from the Google Cloud. We want to keep it in memory, and only as soon as probably a few minutes have passed, or maybe even longer, then we can actually unload it from memory to make space for other bots. So the outcome of this classifier was actually, the precision was actually in the same range as the other one, and it was really nice. It's also fast, but it's also probably because I use more caching. And the training of this model for this large model that with what was it, 77 intents takes about 10 minutes, and it is, I think, pretty acceptable. And in practice, I think 77 intents actually already quite a lot for a bot that has only a few purposes. The memory overhead was also a bit lower than if you would just multiply Python processes, because the embedding service is still quite big, and then there are these worker processes that load the entirety of TensorFlow and a lot of things into memory in Python. So those are about 300 300 megabytes per process. But those Python processes can serve multiple models. So there's not a lot of those. So that makes it actually quite manageable in scale. One thing to notice though with this intent classifier, with this sentence BERT project, was that there was a high false positive rate, and that was something that we did not foresee in the beginning. So if you would have a sentence that was totally out of domain, you have a banking bot, but somebody says, "I like bananas," or something, then the classifier would still, with quite high probability, predict it as one of the intents. And that is because there was no, basically the space around these cluster of banking intents was not really defined. There was no example given of in that space, so it does not really know whether it was better or worse than one of the others. So what we did for that was that we added negative phrases that you maybe also saw in the interface. So for every intent, you can also add negative utterances to intents, and they basically together create like a catch-all intent, which is very broadly trained with all kinds of out-of-domain utterances. And this reduced the false positive rate actually quite a lot. And what also was very interesting was that the classifier was unintentionally multi-language, because the feature, the sentence BERT model that we used was trained on 150 different languages. So actually, when you would say a sentence about banking, but in German, while it was actually trained in English, it would still match to the correct intent. Because you can imagine that with such a big model, it actually, those multi-language models, they are trained on the same texts in different languages all the time. So they know about correlations between words in different languages. This led to some confusion in our clients that said, "Hey, this bot is, I'm talking German to it, but it keeps continuing in English." Well, it should ask like, "Hey, should I switch to German or do it automatically?" But there was no such mechanism in place. And of course, this Q&A classifier now supports multiple bots, which is quite interesting and very nice for our purpose. Some noteworthy Elixir libraries that I used in the process. I already talked about the Erlport. You should check it out. It's quite an old library, I must say, and it's an Erlang library, but it's a really nice way to manage processes that are in the same container. The Python processes managed to Erlang. The other interesting library is called libring. And libring is a consistent hashing library. So it maps some key that you create. For instance, in my case, it was the model name. It can map it to a node and to a worker number in that node. So say I have 8 workers and I have two Elixir nodes in the cluster. So I have 16 workers in total. And then this libring library, you give it the model name and it will always say, oh, you need to be on node A in worker 3. So that way we always load the Python model only once in one specific node. I also created like a small gen server that actually watches the cluster and then update this ring with the current nodes that are in the cluster. I'm almost at I'm actually, this is my last slide, I think. So the future work, of course, when in January, I think, Jose Valim presented his machine learning things in Elixir, I was like, oh, I did everything in Python already. I should have waited a bit. But it still has a long way to go, I think. And the Exxon library is actually progressing really well. But for instance, these large pre-trained models like BERT, etc., they are always stored in the TensorFlow native format, and that is something that is not readable yet by Elixir code. So some parts are still needed. For some parts, Python is still needed, even right now. But actually, what I was thinking, I could also remove these worker Python processes and just do the training in Exxon, but then still use Python code for translating the sentences into feature vectors, and then getting them into Exxon and use a regular classifier there with normal Elixir code. So that is something that I'm actually researching right now, and it's probably going to rewrite it in Elixir, that part. All right. Well, that was my talk. Thank you very much. I would love to hear if there are any questions.
I suppose those of us who are really hungry can head out. But are there any questions? Great.
Hi, thank you for this talk. And before I ask a question, I have to make sure I understand it well. You said that each classifier has to be loaded to RAM. So you have, and it takes 300 megabytes per classifier. So
that is maybe I did not explain that maybe too well. So what happens is there are classifier Python processes that are have the task of classification, but each Python process, because it loads TensorFlow, etc., has 300 megabytes in RAM. But each of those Python processes can load multiple models. So it has like a hash map global where it can load multiple models inside. So the actual overhead of a single intent classifier is only in the tens of megabytes or something. It depends a bit on how many intents you have, etc.
Okay, so when single model is loaded into RAM and it occupies some memory, you can run a few separate classifications using it.
Yeah, definitely. Yeah.
Okay.
But if they end up on the same worker node, then they are serialized. So the classifier and the classification happens one by one, basically. So that creates a bit of latency, probably.
Okay. I just wanted to ask: have you considered? I know you are using TensorFlow, but Torch provides multiprocessing module, which is overridden multiprocessing of Python. And it allows to load one model and reuse this loaded memory between processes.
But then you still would have one model. But the thing is here that, I actually did not look into PyTorch yet. But the thing is here that a normal trained model with BERT, a normal intent classifier with BERT basically built in, is just one. Takes up a lot of memory. So if you would, the thing is that we want to have multiple different models loaded at the same time.
Okay, different, so working in a little bit different way, yes, not the same.
Exactly, yeah, trained on different intents, basically. One is a banking
Okay,
bot.
now
one
I
is
get,
a
now I
bot.
get.
Yeah.
It's clear. And the second question, still a heavy part of your pipelines, I mean BERT featureizer, is something you need to handle because compared to classifiers, it's much larger.
Yeah.
You haven't talked about it. I bet it's not connected with Elixir, so you don't want it to talk about it, but it's a hard thing.
You mean how it works internally?
Once again?
Yeah. Do you mean how the featureizer works internally?
Yes, exactly. How it's optimized, parallelized.
Yeah. No, actually did not. So what I did was I only added a bit of caching to it, so that when the same sentence, because it happens actually a lot that the same sentence is said by with different users or something. But how it works internally, no, that is something that I actually also don't really know, because I'm not that big of a machine learning expert. Actually, I'm just a pragmatic programmer.
Okay, thank you very much.
Yeah, no problem.
We've got one more question from the audience and then one from online.
Hey, great talk. I just have a question about the hardware, just to, yeah, so is it everything, are you using GPU, TPU, CPUs? What goes on the training? What goes on the inference? Yeah.
Actually, right now I use CPUs for everything, because I actually noticed that doing, because there are two parts, right? There's the featureizer part that I basically externalized, and then there's the trainer. And I experimented a lot with TensorFlow with this DNN classifier to run it on the GPU or the CPU. But because the models are so small compared to image processing or whatever, it's actually the overhead of, I guess, putting it on the GPU and pulling it back, it was higher. The GPU was actually it was actually slower to train it on the GPU for some reason.
Cool, thank you.
All right, so I'll read out our online question. Here it is. You mentioned you transfer data from Elixir to Python. Others have mentioned they were able to crash the beam if data was too large. So how much data do you transfer?
I think it is in the order of, well, basically what the biggest payload is the payload that goes from Python or from Elixir to Python, which is the whole training data, which is maybe a megabyte or something, the JSON kind of thing. I did not know actually about that. Is that like a vulnerability in Earlport?
I think good question. I suppose you'd have to ask them what they had in mind in particular, but I think it's just basically too much data period on the wire. Yeah.
Because it uses a port process. Yeah. I don't know. Yeah.
Oh, you're talking about Earlport. I don't know. Yeah. Any more questions?
Me once again. You said you use CPU, so you have a few possibilities of optimization by turning your weights, model weights, to from float 32 to float 16 or integer 8. It's called quantization, all half precision. Have you considered it?
Not yet, actually, because we were actually quite surprised that the training was so fast and compared to previous things that we did. But it could, it probably could be optimized further. Yeah.
Okay.
I also don't know. I think that by default, the sentence, the BERT model returns float 32 NumPy arrays, but it has to be quantized there, I think.